So any questions from the last class? We started recurrence relations and to solve this recurrence Fn equal to Fn minus 1 plus Fn minus 2, to basically find Fn as a function of n that we can understand and calculate, instead of doing this trivial thing, adding it all the way from Fn to F1, we wanted a much faster method. So for that, we introduced generating functions. So yeah, the key thing was that this generating function is defined to be an abstract infinite object which contains all the information about the sequence that you wanted to compute, which is F1, F2, F3 dot dot Fn. And from that information you can, from the recurrence relation, you can actually write down g of t as a rational function. Okay, and then based on that you can expand it into a power series and you can get back what you wanted, which is Fn. Somebody mentioned that there is also a way using matrices to do this. Have you seen that? So what do you think is the comparison between this method and the matrix method? Yeah, but mathematically both the proofs are the same. This 1 minus t square or t square plus t minus 1 that we have, it is actually the characteristic polynomial of the matrix you have seen. Okay, so that matrix, its characteristic polynomial is what appears here, and hence 1 by alpha, so these alpha beta are actually the eigenvalues of that matrix. Okay, so whatever you do with the matrix, you can as well do with this. Okay, it is just a translation of this notation that we have done here. It's not a significantly different proof. Yeah, and we will not use float to compute this alpha to the n plus 1. If you actually have to implement, you will implement it similar to the matrix method. Nobody will actually use square root 5 float value to compute this. There are better ways. In fact, you can treat square root 5 as a kind of a variable. You don't need to write down square root 5 as 2.2 or whatever. Okay, you can treat square root 5 as a variable and then you can compute alpha to the n plus 1 in a systematic way. So I will not do that, but let's proceed with the other kinds of linear recurrences, unless you have a question. So yeah, this is a powerful method for linear recurrences. Okay, so linear recurrences look like this Fn equal to Fn minus 1 plus Fn minus 2, except that this may be any previous values and any linear combination. So for example, it can look like your Sn can be Sn minus 1, Sn minus 2, Sn minus k. Okay, it can go to much further away than just n minus 2, and also a1 to ak you can pick. So previously they were all 1 or 0, but this can be anything now. So for A1, A2, AK and K constants. So what does constant mean? Is n a constant here? Yeah, n is the only variable here. N is going to infinity. Everything else is constant. So you have to pick A1 to AK and K to be independent of n. Okay, that is what we will mean by constant. For constant, there has to be a contrasting variable. In this case, the variable is n. So you can take n to be anything given A1 dot dot AK and K. So like you can take K to be 100 and you can take A1 to AK to be any integers, and after that the recurrence holds for any n. So what will be the solution of this Sn? From the previous experience, what will you get? Yes, so like you got combination of alpha to the n, beta to the n, there were 2 powers. Now you will have k powers. So yeah, we can briefly discuss that, but we will not go into the details of this. Details are similar to what we did before. So let gt be the generating function of Sn and everything, and you want to write now gt as a rational function, and then after that you want to go back to Sn, right? So from Sn you go to generating function, and from that you go back, right? That is the general strategy in this chapter. So like before, like for Fn, we can write or deduce that gt will be a rational function which will look like this. It will define a polynomial in the numerator and a polynomial in the denominator. So in the numerator you will see b up to t raised to k minus 1. Is that right? Yeah, something of this sort. You will have a polynomial of degree at most k above, and below you will have a polynomial of at most degree k. Okay. For yeah, so this A1 to AK is the same actually, which appears in the recurrence. It isn't a mistake. Okay, and additionally there will be these other constants B1 to BK that you will get from the generating function. Any questions? I think this is what you will get. What will B1 to BK depend on? Yeah, so B1 to BK we don't know because we have not specified how Sn begins, right? So what is S0, what is S1 dot dot. Based on those values you will get B1 to BK. AK to the TK. Yeah, that's a minus. And this then you can write by, you again denominator you factorize, you will get k roots, and you can write it potentially as, sorry? ak raised to it has to be shifted. Yeah, that may be right. And this is tk, right? Okay. Yeah, so in the simple case it was 1 minus t square, same thing. And this you may potentially write like this, 1 over, or not, maybe not 1, c1 over 1 minus alpha 1 t, and there may be k roots, so you will get this. Right, where alpha 1 to alpha k are what? Where the denominator factors as 1 minus alpha I t, I1 to k. Okay, so in the case when, okay, so in general, will every polynomial have these k roots? Yeah, so prove this as an exercise that this is always possible over complex. Over complex, there exist roots alpha 1 to alpha k. Okay, this I will not prove. What is this theorem called? Yeah, this is the fundamental theorem of algebra. Although the proof is hardly algebraic, it's by analysis. So you can try to prove it and then read the proof. So any polynomial can be factored into these roots, as many as the degree. When can you write this as this sum of 1 minus alpha I t that I have written? When is this possible? Is it always possible? Right, so also show that when alpha i's are distinct, then that representation will exist. So this exists if alpha i's are distinct. Okay, so this is actually the easy case. The proof is the same as we did for Fibonacci sequence. You will get the same, I mean in this case, you will again take the LCM and C1 you will multiply with a k minus 1 degree product. And you will again see that the number of unknowns is k and the number of constraints is k, and you can solve it. But if alpha i's repeat, for example, if all the alpha i's were equal, then you are looking at 1 minus alpha t raised to k, right? And that will have a very different behavior. So do you know what happens then? Right, so suppose the denominator is 1 minus alpha t raised to k. So in that case, what can you do with this? Then you have to expand 1 over 1 minus alpha t raised to k in a power series. How do you do that? Yeah, so you can again use binomial coefficients. Slightly more general in general form, what you will get is 1 plus, okay, you can see this as 1 minus alpha t to the minus k, right? And let us just blindly do the binomial expansion without worrying about minus k being negative. So if you blindly do that, what will you get? Minus k, choose 1, plus minus k, choose 2, and you do it n times. Okay? And what is the meaning of minus k, choose n? Where we are saying that minus k, choose n stands for minus k minus 1 minus n plus 1 divided by n factorial, right, which is minus 1 to the n times n plus 1 minus k, choose n. Okay, which is a well-defined quantity, usual binomial coefficient. So what you are getting here is, instead of n choose k, you are getting something slightly different, but you can check that this is correct. In particular, for k equal to 1, what happens? Yeah, for k equal to 1, you are getting n choose n, which is 1. So that's correct, right? And you can see that for k equal to 2 also it is correct, and in general, you can prove this. I mean, in the world of power series, this is an identity. This calculation is correct. And n plus k minus 1. Okay. So the coefficient of t raised to n that you are always interested in this generating function or in this rational function expansion as a power series, this is is there a problem with the sign? Oh yeah, I was just expanding as a binomial series, so I should have put minus alpha t then. Yeah, so now the sign will be fine. So now the coefficient of t raised to n is n plus k minus 1 choose n times alpha to the n. Okay, so you can see that this is fine for k equal to 1. You are getting alpha to the n as the nth coefficient of t raised to n. So hence any kind of a rational function will be fine. Okay, you can have powers or you may have products. Ultimately, you can get to the point where you will know each and every coefficient in the power series, and hence you will know what Sn is. Yeah, so maybe we finish with that. So what we have shown is this kind of meta theorem that linear recurrence for Sn implies that Sn is a it's a linear combination of of functions. Example, you have, if the roots are distinct, then you will have alpha I to the n, and if alpha I was a, or if alpha j was a repeated root, then you will have you will have some power, n to the j, maybe alpha I. Okay, so whatever is the, okay, let me call this maybe m. So if alpha I is a root that doesn't repeat, then you will get alpha I to the n in the place. I mean, you would express Sn as a linear combination. So in the place, in the ith place, you will get alpha I to the n. Otherwise, if alpha j has a multiplicity of m, it repeats m times, exactly m times, then you will get things like n to the m. In fact, let me not say m is the multiplicity, this can be anything. Anything below the multiplicity. Is the statement clear? Maybe if you want to see this, you should use this identity here, n plus k minus 1, choose k minus 1 times alpha to the n. So what is happening is that the k comes from the multiplicity, so it is something fixed, and then this binomial expression, this has n to the k minus 1 appearing, and also n to the k minus 2 appearing, dot dot n to the 1 appearing, right? So you can see this coefficient calculation as a linear combination of n to the k minus 1, n to the k minus 2, dot dot n to the 1, n to the 0. So ultimately, linear recurrence means that you can ultimately solve and get a linear combination of functions which are either powers of the roots, or you are multiplying by some power of n. Should not say alpha I, it's alpha I to the n. So exponentiation and multiplication by a power of n, right? That's a mixture of this is what you will get. If this is not clear, you can take it as complete the proof as an exercise. So for example, Sn could be 1 plus, it's a linear combination, so maybe C1 plus C2 times 2 raised to n plus C3 times 3 raised to n plus C4 times n times 3 raised to n. Let me further fix C1. So if you look at this this function, there will be, you can actually conversely express a linear recurrence for Sn of the type that we discussed in general. Okay, so it goes both ways. Linear recurrence implies such an expression implies linear recurrence. And for this, what do you think will be the depth of the recurrence? How many previous values are needed? Yeah, so you can see that for this you will need Sn minus 1, minus 2, minus 3. Yeah. K equal to 3, I guess. Or K equal to 4. It could be K equal to 4. Because this root 3 has multiplicity 2 and 1 and 2 have multiplicity each 1. So you get 1 plus 1 plus 2. So you need 4 previous values to deduce Sn. That will be the linear recurrence. So you should be able to get values for A1, A2, A3, A4 from this. I think all the values are non-zero, all these 4 AIs. So you need 4 values, 4 previous values. Is that clear? So unless you work on this, you will not understand what just happened. So do some of these things as an exercise. Okay. So now we will look at a more complicated generating function. So what happens if this generating function that we are looking at, GT, it is not a rational function? Right, here we were targeting big G of t to be a rational function, so that we have this general method of converting it or re-expressing it as a sum of simple things like 1 over 1 minus t or 1 over 1 minus t square, and hence get the power series representation. But what if this G is not rational? For example, if it is e raised to t, what happens then? Do you know the answer? Example, gt is e raised to t, or suppose it is e raised to t. What will happen then? Or more interestingly, if I give you an Sn which doesn't have a linear recurrence, I give you a non-linear recurrence, how will you handle it in general? Right, that's the next question, and we'll see actually many simple examples where that actually happens. So what is the meaning of the recurrence being non-linear? Yeah, AIs are not constants, which means what are they? Yeah, they are dependent on n. So for example, Sn equal to n times Sn minus 1. Right, that means that this Sn is growing very fast. And the solution is what? Yeah, in that case it's n factorial. If I give you Sn equal to n times Sn minus 1, then what Sn is n factorial. And now if you see the generating function of this, it's very complicated. You will not be able to simplify it. So the GT of this is 1 plus 1t plus 2 factorial. So this is 1 factorial, t square, 3 factorial, t cube, and so on. Right, but you cannot express it as a rational function. It will not. You can show that it's impossible. So there will actually never exist a linear recurrence for this Sn, for n factorial. So weird things happen. So the examples that we are studying in this chapter, in this class, these are not exhaustive. Okay, many worse things are possible. But we'll only focus on the good things. We'll shield you from the bad examples. So let's look at another nice case which we can potentially analyze, that's called exponential generating function. Okay, so let me shorten it to EGF. So in some cases, when essence recurrence is non-linear, we can analyze using EGF. So this will be a more complicated analysis. So let's start with an example, okay, and then we will see what EGF does or what it is. So let us consider this example, counting example, where let's say you are given so first of all, what is an involution? So involution is a permutation that so okay, let me say domain also is a permutation on the elements 1 to n, such that for every I, either I is fixed or there is a j where I and j are flipped. For every I in 1 to n. So okay, let's also name this permutation, let's call it pi, sigma, such that either sigma fixes I or there exists a j such that sigma is swapping I with j. Is that clear? So the map where 1 is sent to 2, 2 to 3 and 3 to 1, is that an involution? So the map which sends 1 to 2, 2 to 3 and 3 to 1, is this an involution or not? Because the reason is that 1 is an element, if you take I to be 1, 1 is not fixed and there is no j such that 1 and 2 are flipped, right? Because if you look at 2, 1 is mapped to 2 but 2 is not mapped to 1. If you look at 3, 1 is not mapped to 3, only 3 is mapped to 1, right? So this is not an involution. An example of involution is easy. You can just say 1 is mapped to 2, 2 is mapped to 1 and 3 is fixed. Right? So now the question is the obvious one, how many involutions are there? Sorry? Yeah, sure, we will use recurrence. But so the total number of permutations is n factorial, right? So what do you think, how will the number of involutions be close to n factorial or far away from n factorial? Yeah, intuitively it should be much smaller than n factorial, but again we don't have a concrete idea. So what we will show is as expected, we will write down a recurrence. It will look hard. It will not cannot be solved using the previous methods. And then we'll use some differential equations, and then we will find the like a good estimate for the function, for the number of involutions. Okay, that it will be actually involutions will be a lot, not n factorial but still exponential. Yeah, so let us write down the recurrence. So let In be the number of involutions on 1 to n. Right, and this clearly will be less than equal to n factorial. The number cannot exceed n factorial because the total number of permutations is n factorial. So it will be much smaller than n factorial usually. So what is that? Okay, so what is I0? I0 we can just set by convention, so conventionally we call it 1. It doesn't matter for now. What is I1? I1 is, yeah, one, there is only one permutation, it's an involution. What is I2? 1, 2, again, 2 permutations, both involutions. And what is I3? Sorry, I shouldn't say definition. These are equal. What is I3 on 1, 2, 3? Yeah, that you have to check. It's 4. So the examples are you don't do anything, that's identity, or you flip 1 and 2, or you flip 2 and 3, or you flip 3 and 1. Right? These are the 4 involutions. And everything else is a cycle, right? Like 1 goes to 2, goes to 3, goes to 1, and so on. Okay, now with this experience, can you write down the recurrence? What is it? I mean, what is the argument? So we again want to use the sum rule. What are the two summands? How do you divide your cases? So in the definition it says that either I is moved or either I is fixed or it is moved to some j, right? So what happens if I is fixed? Well, let's just fix I to be n first. So consider the last element, and the cases are, first case is n is fixed, is not moved to any other element j. So this means, so how many permutations are there? So number of such involutions n is fixed, everything else can do whatever they want to do, right? Up to involution. So that's I of n minus 1. N is moved to I, to j. Well, not moved but swapped. N swaps with j, what is the number of involutions? Yeah, let's fix j to be 1. So if you are swapping n and 1, or any j you fix and then you are swapping n and j, so these two, the permutation is defined, rest it can do whatever it wants up to involution, right? So that's n minus 2. So till now it seems like the Fibonacci recurrence. The difference is that j are many, right? So number of j's is, it is n minus 1, right? So now what you get, now all these n possibilities, they are disjoint, right? You are not getting the same involution in any of these cases. So you can do the sum rule and you will get In is equal to n minus 1 plus n minus 1 times I n minus 2. Is this clear? Any questions? Okay. Right, so this is, in a way it is similar to what we did with Pingla's proof. But unfortunately the recurrence you get is far more complicated. The only complication arises because of this. Right, this n minus 1 is not a constant. This is why I said the meaning of constant or definition of constant is it should be independent of n, but here it depends on n. So as n grows, this coefficient keeps growing. So this suggests that it will be growing much faster than Fibonacci series, right? And it also suggests that it will be growing slower than n factorial. Is that clear? But what exactly is it, we don't know. Just from the recurrence we can't deduce this. And that will be complicated to deduce actually. So okay, you just to understand more properties from this of In, you can, this is non-constant. But as an exercise, you can try to show that for n at least 2, In is an even number. Can you see this? How do you show that In is even? It's always even, except the boundary conditions which you already wrote, 1 and 1. So you can show this by induction. Right? See, check it in the base case, which is 2 and 4. Then from there you can easily deduce. And you can also show that In is greater than square root of n factorial. Okay, so it grows very fast, but still could be smaller than n, I mean far away from n factorial. It's at least bigger than square root of n factorial. Try to show this. It's a good practice of induction. Okay, so yeah, do you know what is the generating function that we'll use for this? No, EGF, but what is the modification we'll do on G of t? Yeah, so for some reason, it's not very clear at this point why. We will use the following GT. It will be In t raised to n And so this would have been the usual generating function. In the EGF case, what we will do is we will normalize it by n factorial. Okay. Yeah, as I said, it's not very clear why we did that, except that if in was 1, it will be what? If all the ins were 1. Then it's e to the t. Then you can deduce that g of t is equal to e to the t. Okay, so the reason why we did this is we are now moving from rational functions to the next family, which is much bigger than previous one, where we'll try to get something like e raised to t. And luckily this will fit for involution. So, and yeah, hence the name exponential generating function. Okay, the exponential comes from this basic case of everything being 1, then it's e to the t. Maybe a more relevant reason is that since you have n minus 1 multiplying there, if you divide by n factorial, then somehow it will try to deal with that coefficient n minus 1. As I said before, if it was just n minus 1 times in minus 1, right, then you would have gotten n factorial. So if you divide by n factorial, then you will be measuring how far is in from factorial function. Okay, so that may be a relevant reason, but it's not enough. The real reason is that you are getting lucky. So let's see why is that. Okay, maybe I should call this something else. It's theta. Okay. So, yeah, so what you do is now differentiate this. Okay, so d by dt of theta t is what? Sigma in times t raised to n minus 1 factorial, right? N going at least n greater than or equal to 1. And yeah, now use the recurrence for in. So what you will get is n minus 1 plus, what was it, n minus 1 so do you see some simplification here? This in minus 1 by n minus 1 factorial is of a good form, right? This is again theta. And the second one, that is almost theta, because you again get n minus 2 by n minus 2 factorial. But the t is what is a bit shifted ahead. So we multiply by t, right? So you can see that this is equal to theta t, or maybe I write. So you get in minus 1. So this thing plus I take t outside. So it's I n minus 2 n minus 2 by n minus 2 factorial. Is that clear? So things are a bit shifted, but you can see that ultimately they are just theta, each of these. That was the magic of you defining theta t. So you get theta t plus t times theta t. Right, this is the derivative of, this is equal to theta derivative. What do you do next? How do you find theta now? Sorry? Yeah, this is a differential equation of a very simple type. Here the derivative of theta is a multiple of theta, and there is a systematic way to do this. You divide theta derivative by theta, go to log, and then you will be done. Then you integrate basically. So you write this as d of log theta, which is equal to 1 plus t. And when you integrate, what happens? When you integrate, you will get log theta is equal to t plus t square by 2, that's all, or something else? Yeah, there is also an unknown constant. So which means that theta t function is exponential. Is that clear? And how do you find c? Yeah, initial conditions. So you let us just set t to be 0. What will happen? T0 will be I0. So I0 has to be equal to e to the c. What was I0? That was 1. So you get C0. Right? So then theta t is perfect. It's e to the t plus t square by 2. Is that clear? So the involutions, when you write this infinite object, the EGF, that comes out to be exponential of a polynomial, right? And you know how to expand it, you know the formula. So that will give you now involution. So now you can use this to compute coefficient. Well, you want to compute In, which is in fact In by n factorial, which is the coefficient of t raised to n in e raised to t plus t square by 2. Okay, so you express this powers of t plus t square by 2 in the e raised to x expansion, and from that you extract, from every power you extract t raised to n. So that will give you a good idea of what In is. You multiply that by n factorial and you get the function. I mean, obviously this is far away from a closed form, but if you wanted to write a fast algorithm, this will help. Any questions? That I1 is equal to 1. That is true. So where was that? Well, in this calculation here, did I need I1 equal to 1? Yeah, it's not clear whether, yes. Yeah, but what he suggested is more direct. He's saying that if you look at the recurrence and substitute n equal to 1, then it I1 only requires 1, the previous value. So as soon as you fix I0, everything is fixed. No. So the recurrence, once you have the recurrence, you have the algebraic expression. So you don't need, you just have to check whether what is happening at the boundaries. So the boundaries will be, in this case, the boundary is only I0. After that, I1 follows from I0. It's not that there are two boundaries. See, everything that happens in the calculation only requires the truth of this I0 equal to 1 and this equality, the recurrence, that's all. It doesn't need I1. No, look at the recurrence. The recurrence says that I1 is equal to I0. Doesn't matter. Once the recurrence is written, it's written in stone. You just have to do the calculation following that. Yes. No, so obviously you can implement it, but my claim that it will be fast, that we have to check. How will you implement it fast? Will it be faster than the recurrence computation one step at a time? No, but this alpha to the n plus 1 wasn't a closed form. For Fibonacci sequence also, that wasn't a closed form. Because if you just substitute square root 5 as the real number, computers don't really work with reals, right? It only works with fractions. So that is also not a closed form. That is why I said you have to implement square root 5 in a discrete way. You cannot think of it as a real number. That will not work. No, but see. Correct. No, then the recurrence is false. Then you cannot do whatever we are doing post recurrence. Yeah, that's not needed because there is a 0 multiplying. No, but at n equal to 1, the product is already 0. Why do you need, there is no reason why you need n equal to 2 or more. So as I said, you just check that once the recurrence is written, it's everything else follows. If it is a paradox, then the resolution is that it suffices to assume I0 something. You just assume I0 to be, you can assume for example I0 to be -1. After that everything else will just develop based on the recurrence. There is only one boundary condition, not two. So we picked I0 1 because that is the only thing that makes sense for involution. But we could have picked it to be -0.1. Right? Even -0.1 is fine for I0. Everything else will follow except when we fix C, that will then change. There will be an issue that -0.1 equal to e to the C, then what is C? Right, so that's the only problem, otherwise everything is fine. Okay, so I think our time is up. If there are any questions, you can ask me later.